Hey, good evening.
Hey, good evening.
Yeah, your mic's a little bit low, Gerald. Why don't you bump that up a little bit?
All right.
That's better. Great. Well, I'm Rich Ozer, and Gerald McKeegan is here with me, and John Curry will be here in just a sec. He was chasing down some lights that were still on the deck, so now that those are extinguished, he'll join us. Welcome to our first virtual telescope for the month of June.
Yeah. It's
And
a little bit windy tonight.
Yeah, it's windy, it's cold, and it is just below our humidity level that we at which we have to cease operation. But what is it at right now, Gerald? We're
82%.
82%.
So
So if
as
it
long
hits
as we,
85, then we have to consider closing our
yeah,
our dome here or our roll-off roof actually, and hopefully it'll stay below that.
yeah,
Um,
unless of course we happen to be seeing one of those UFOs that the Air Force has been talking
All
about.
right.
We might
that's
stay
right.
open a little bit longer.
And now
Just
we're going to get a bunch of questions about those, Gerald.
No doubt. Yeah, yeah. That's the
I know
beginning.
nothing.
Hey,
Yeah,
guys, sorry I'm late. Had to go turn the lights off.
yeah. So, we're at the Chabot Space and Science Center, and we are operating the 36-inch research reflector telescope known as Nellie. I want to remind everyone that the Chabot Space and Science Center is still closed because of the pandemic, and is planning on opening in the month of November to the general public. So that's the plan right now. We have some limited events that are still happening on a week-to-week basis, private events, small weddings, that type of thing. But as far as opening to the public, we have to wait till November. So in the meantime, we depend on donations from viewers and people in the community. And I want to thank Fremont Bank for sponsoring our particular program and others. So if you are so inclined, please hit that donate button, and you'll see it on the Facebook page on which you're watching the video. And if you'd like, you could visit the website at www.chabotspace.org, and it will give you all kinds of information about membership and donations. So with that out of the way, I guess we can get started. Gerald,
Yeah.
I was,
Hey, Richard,
yeah,
would you
yeah.
explain why it is that you're black and white?
Oh, uh, well, one of the things I've discovered in the part of the observatory that I sit in is that it's particularly dark because Gerald's got a nice red light that's on the desk that he works at and another light. John has a bright enough screen where it illuminates his face. And in my case, the video keeps cutting out. So I picked up a camera that does infrared. And so I'm being illuminated by an infrared camera, and it's working quite well. I used this a couple of weeks ago during our lunar eclipse event all night, and it doesn't cut out. So that's why.
That's
Um,
pretty good. We
I don't.
just answered our first question on Facebook here. Why Richard
What
is
was
in
that?
black and white.
Oh, there you go.
Yep.
Yeah, that's because I'm back in the 50s.
You might also hear
Yeah.
that there's a bit of wind on our microphones tonight. It is a bit breezy up here, and that might affect our seeing a little bit. So,
Yeah.
uh,
Just a little bit.
just a little bit. You might
Yeah,
find our stars are a little fuzzy tonight or
yeah, they
wobbly.
are. They are a bit fuzzy. So while I'm getting set up here on the camera, Gerald, there's an event later on this month that people might be interested in learning about having to do with asteroids.
Yeah, on June 30th. June 30th is what we call Asteroid Day. It's an international celebration uh, about asteroids. Started out to celebrate the efforts to discover near Earth asteroids, and it's kind of expanded a little bit to just talk in general about asteroids. And various science institutions around the world hold different events, and we are going to hold one right here at Chabot Space and Science Center on June the 30th. And we will have some guest speakers talking about asteroids, and we'll talk a little bit about how we find asteroids and a little bit about what the threat is to the Earth, and show some pictures and take some questions. So something to look forward to. And that's going to be again on the evening of June the 30th, which I believe is a Wednesday evening.
Yep.
So you want to join us then?
That's the day after Election Day. We have a special election here in Alameda County, so don't forget to vote.
All right. Well, Richard, you got your camera working yet?
I do, and right. Let me go ahead and switch to that.
So
and
right
what
now
star are we looking at?
We're looking at the star Denebola. Denebola is a moderately bright star in the constellation Leo. It actually forms the tail of the lion. So it's a nice star for us to get started on, because it allows us to focus the camera and get everything aligned and everything. So I was thinking if we went from here right on over to a globular star cluster called M3, it's not too far away. So if you guys agree, I'm going to go ahead and slew the telescope.
Go ahead.
Go right ahead.
I think it's going to be globular cluster night.
I think you're right. We'll do a few globular clusters, and maybe or later on we'll catch a planetary nebula, a very unique planetary nebula. All right, Richard.
Okay.
You'll need to do about a 30-second exposure.
Yep.
So what we're looking at is the globular star cluster M3. It's I like to say it's in the constellation Boötes, but I think technically it's in the constellation Coma Berenices, which is right next to Boötes. It's kind of on the boundary between the two of them. One of the distinguishing stars in Boötes is the star Arcturus. And if you go outside right now and look straight up in the sky, if you're here in the Bay Area, you'll see kind of a yellowish star almost straight overhead. And that is the star Arcturus in the constellation Boötes. And the globular star cluster we're looking at is just a little bit northeast of that star. So in just a second here, I think we're going to see an image.
I hope so.
And the answer is,
yay!
Boom! How about that? Right smack in the center.
Yeah,
there it
job.
Is. So,
wow.
Globular star clusters are huge groups of stars. They're very old stars. The stars in the cluster are orbiting around the center of the cluster in highly elliptical orbits. And then the cluster itself orbits around our galaxy in a region called the halo of the galaxy. So if you imagine looking at the Milky Way galaxy from outside of it, it looks like a flat disk with spiral arms in the disk and a central bulge in the middle. And around all of that, you'll see a very diffuse, faint region we call the halo. And the halo is composed of a lot of old stars, most of which are very far away from each other. But also in the halo is about 150 of these globular star clusters. And these are leftovers from the formation of the galaxy. When the galaxy was first forming, something like 12 billion years ago, it started out as just a big, huge cloud of gas and dust. As that cloud began to condense, it didn't condense in a nice uniform way. It condensed into clumps, and it began to start rotating and eventually flattening out and becoming a disk. But some of those clumps got disrupted as the galaxy started absorbing nearby small galaxies, and those clumps ended up out in the halo region. And so that's what you see here, is that one of the star clusters, globular star clusters, that resulted from those clumps of gas and dust very early in the formation of the galaxy.
Now, this is a particularly large and bright globular cluster and probably has upwards of a couple 100,000 stars.
Right. Yeah.
And
Close to 400,000 stars.
yeah. Oh, 400. That's
Yeah.
even more than I realized. Yeah.
Yeah. Now, we give you a number like that. We're going to look at 2 or 3 globular clusters tonight. We're going to tell you, well, this one's got 400,000 stars and that one's got 500,000 stars. Understand that this does not mean that some poor astronomer is out there counting each of those individual stars.
But Gerald, I thought that was your job.
we have a much less precise but much easier way of determining the number of stars. As I said before, the stars in the cluster are orbiting around the cluster. And by studying those stars carefully, we can get a pretty good idea of how far away they are. And if we know how far away the cluster is, and we know how fast the individual stars are orbiting, we can use that to calculate the mass, the total mass of the star cluster. And we come up with a number that's a very big number. And then we make a huge assumption. And that huge assumption is that our sun is an average size star, an average mass star. So you take the computed mass of the entire cluster, you divide it by the mass of our sun, and you say, okay, that's how many stars there are in this cluster. So take the number we give you with a little bit of a grain of salt, because if it turns out that there are more than the typical number of low mass stars, then there's actually more stars in the cluster. If it turns out that there's more than the typical number of high mass stars, then that means it's fewer stars in the cluster. So if the average mass of the stars in the cluster is the same as the average mass or the mass of our sun, then it's about 400,000 stars.
That's a good explanation. Thanks for that.
Right.
Yeah. Good. If you want, we can now take a look at M13 to compare it a little bit.
Okay.
And why don't we let this one exposure finish here, 5 more seconds. And maybe I'll stack these up for next week. All right.
Okay, I'm going to take an intermediate stop along the way here on Gemma, which is a double star in the constellation Corona Borealis. So, are we ready?
Yeah, go for it.
Okay. So when we make big moves with our telescope, it's computer controlled, and the computer tracks pretty well where the telescope is pointing in the sky, but it's not 100% perfectly precise. So when we do big moves, we like to stop at an intermediate point along the way and make sure that our telescope is nicely lined up. And so this is the star Gemma. It's in the constellation Corona Borealis, the Northern Crown.
Also called Alphecca. It's got 2 names.
Yeah. Okay, so we found that. We're centered up on that. Now let's go see M13, the Great Globular Star Cluster in Hercules. And we are there.
Okay, and we'll do another, we'll do 30 seconds again.
So this is a little bit bigger globular star cluster. It's got about 500,000 stars, and some people think it has maybe even more than that. I've seen estimates as high as 1 million stars. Most of the papers that I've read suggest it's somewhere in the neighborhood of about 500,000 stars. So
these numbers have been going up since I first started doing astronomy.
Yeah, I took a.
Gerald has been counting them, and
he keeps revising his data.
Yeah. Oh yeah. When I took my first astronomy course a long time ago, The instructor told us that these clusters had only about 10,000 stars in them. So
Yeah, there you
things
go.
have changed. Okay, looks like we need to shift a little to the north.
Yeah, it's a little bit too high there. Maybe we can.
Okay, try it again.
Yeah, you know what I'll do is I'll take a 10-second one just to see if we got it centered, and then I'll bring it back up to 30.
So the neat thing about M13, it's in the constellation Hercules. It's one of two fairly bright globular star
good.
clusters. Yeah, there you go.
Yeah.
So now doing a nice long one. This is one of two bright globular star clusters in the constellation Hercules. But we like this one the best because it's really easy to find with a pair of binoculars, or if you're using a small telescope and it's not computer controlled, you're having to manually point the telescope. This is a really easy globular star cluster to find. There's a region in the constellation Hercules, 4 stars forming what we call the keystone. It's when we see patterns like that within a constellation, we call it an asterism. And the keystone is 4 stars in kind of a trapezoid pattern. And this star lies right on one of the edges of that trapezoid, right between 2 of the stars. So it makes it very easy to find M13. It's another one of these globular star clusters. It has an unusual feature to it, which makes it very easy to the experienced eye to recognize as M13. It has a 3-bladed propeller in it.
Right there.
No,
That's it over there.
No, to the left. Lower left corner, right there. Nope. A little farther.
Almost there. A little up. Over to the right, just a little bit.
Up
to the right.
Right to the little. No.
Man.
Fork right there. Stop.
Right there.
You're right at the center of the propeller.
I'm moving
right
this
there.
so I can see it.
Yes.
The
experienced eye.
Not the experienced eye here, because I'm not seeing that at all.
Okay, so there's
you had the cursor right in the center there.
Yeah, the one blade going up, one blade going down and to the left.
Oh, I see it
going
now.
down to the right.
Oh gosh.
So
I was seeing a cross over here, and I was thinking, oh, that must be the propeller. And I see it now here, and down like this, down like that.
There you go. All right. So this is actually caused by gas and dust within the cluster, which is an unusual thing to begin with, because these globular clusters tend to not have very much gas and dust. But it forms that pattern that we call it the propeller. It's one of the distinguishing features of M13. All right.
Yeah.
One more to look at in the constellation Hercules.
The other Hercules cluster?
The other Hercules cluster, yeah. And then
That's
after that,
M96, right?
M92.
M92.
Yeah, M92. Then Richard's going to wow us with an image of the champion of all globular star clusters.
I'm going to take a short one just to make sure we're centered. We should be.
Yeah, we didn't have far to go for that one.
Yeah.
Yeah, that should be pretty much on target.
And the answer is
patience.
It's a little high.
Oh, gee. How about that?
I don't think you synced on the last one.
I thought I did, but maybe I didn't. All right, try it again.
All right. You know what they say, sink or swim.
So this one's a little farther away. M13 was about 25,000 light years away. M92 is
There
about
we go. That's nice.
30,000 light years away. So a little bit farther.
All right, we'll take a
All
longer
right,
one
now do
Yeah.
a long exposure. Yeah.
Yeah, I mean, these are really notably different. I mean, visually, when you compare M13 to M92, M13 is like a much more symmetrical and filled out object,
And brighter.
and brighter. But
Yeah.
this one is not as spherical looking. It looks like it's gone through something in its history that's caused some distortion. But it gives you some idea of the variety. These don't all look the same, just like
There you go.
there it is.
Yeah,
Got
that's
a little
better.
lost a little focus a little bit on
Yeah,
this. Maybe
either
we'll
that
try
or
another one.
just
I could be seeing
wind.
Yeah, the wind might have picked up right when I was shooting. Yeah, we are dealing with a breeze tonight.
We can actually hear it blowing across the microphones.
Yes.
Oh.
Yeah, we were shopping on Amazon before we started tonight for
By the
foam
way, guys,
covers for our microphones.
We're at 84%. So.
I noticed that. I sent a chat out earlier and didn't
Good to know.
Oh, did you?
want to mention it, but yep.
So the reason we worry so much about the humidity is because if the humidity gets too high, we'll get condensation on the telescope, and that can cause us a couple of problems. Of course, if you get condensation on the mirror, the telescope, then everything starts to get really fuzzy. And there's some electronics inside the telescope, and getting condensation on electronics is never a good thing.
But the worst thing is,
when the mirror gets wet and the dust settles on the mirror, and when the mirror dries, the dust is still there.
Yeah,
it's glued to the mirror.
Yeah, and Gerald has to get on his hands and knees at on the mirror and scrub the mirror
with little tiny cotton balls. It's no fun.
Yeah.
And it's really dangerous for the mirror.
Yeah. Not to mention the person scrubbing it.
Yeah. You never want to be under the mirror when you're scrubbing it.
No, you never want to be under the mirror. That's right.
The mirror in this telescope weighs about 500 pounds.
Yeah.
So, yeah, you don't want to do that.
So I'm not sure whether it's a focus issue or whether
it seems like the focus got soft, but
yeah,
it's hard to say. So maybe we'll take a detour on the next object and check our focus.
All right.
Who was it at Lick who ended up having to spend the night in the telescope tube because he had fallen in? Well, it was Crosley, right? Wasn't it Crosley who was doing a night of observing? And he loved to smoke cigars, and he dropped the cigar, and cursed and said, "I got to go and fetch the cigar." And he goes crawling down the tube, and of course, now with the added weight of Crosley, the telescope turned into a mousetrap. And it trapped him at the bottom of the telescope, and he was sitting there on top of the mirror the entire night until someone found him in the morning.
I never heard that story. That's hilarious.
Yeah. So don't let that happen to you, Gerald.
What telescope was that?
I've only seen
it was a mirror, so
I think it was the Crosley telescope. Yeah.
Okay.
Yeah.
That makes sense.
Yeah. I don't think that's the incident that caused them to name it after him.
Well,
I mean, if that's all it takes to have a major scientific instrument named after you, then, excuse me, I've got something I got to do right now.
All right. Okay. So, Richard, you want to first do some focusing here, or?
Yeah. Let's.
Okay, let's go to an individual star.
I have to abort the current shot here and move over to frame and focus. It'll take just a sec.
Hey, let's look for a good star for you, Gerald.
Yeah, really
I got
anything.
How about
one.
Vega? We're very close to Vega
Well,
already. Oh,
that's a
that might
little
be.
too bright.
Yeah, I
Yeah,
got a second magnitude star here. It might be
yeah.
better.
I
Okay,
think so.
ready?
Second or third. I'm ready.
You go back to Gamma.
All right. Yeah,
All
it
right.
sure does look like it's softened up.
That's not gamma, by the way.
No.
Okay.
Do you want to use the paddle, Gerald, to
I've
focus
got
it?
one here.
Yeah. All right.
All I gotta do is get you out of the way here because your image is right in the way of what I'm looking at
Hold
here.
on. Let me. Oh, you mean?
No, it's okay.
I'll
All right.
duck.
All right, that's okay. That's a little not too far.
Wrong way. Yeah.
Boy, you're
Yeah.
kind of
It's
all
just
around it. It's not.
it's just that the
That's about the
seeing. I
best
think
I'm gonna
it's the
get.
best we're gonna get. It's probably that the
Yeah.
seeing really softened, and it wasn't the
Yeah.
focus on the
Yeah.
telescope as
You
much.
look at you look at that zoomed in image, and it's just bubbling and moving all around.
Yeah. Yeah.
Yeah, when we talk about seeing, what we're referring to is the quality of the image resulting from atmospheric distortion. And you could see that because of the high amount of moisture in the upper atmosphere tonight, not to mention, probably moisture in the lower atmosphere as well from the fog that's trying to come in, you see how things are moving around. It's like you've got your head underwater looking at a light at the other end of the swimming pool, and that's considered poor seeing. If that was, more of a pinpoint light and not moving around so much, we'd consider it good seeing. And good seeing is better for visual observing and for photography. So, it's one of the negatives of being in the Bay Area is that the seeing can get poor pretty quickly because the microclimate changes very rapidly. But there's places nearby we can go that avoid it. But we can't drag the 36-inch telescope with us. That's the problem.
And I was just pointing out to Gerald that we are looking like we're having a humidity problem here. We're at 85. We're right at our limit.
All right. Well,
I'll tell you what,
might
Rich,
wait
you've got that other globular star cluster that you wanted to look at. You got a picture of it?
yeah.
You
Let's
wouldn't
do
be
that,
able
and we'll
to
wait
see
and
with
see.
this telescope?
Yeah. Hold on for a second. Let me stop sharing. Okay. We're all back now. Let me. All right. So what I'm going to show a picture of is the globular cluster Omega Centauri. And let me go ahead and share my screen.
Oh, why can't we look at that?
I'll explain that in a second. All right. So, you guys see that?
Yes.
All right. So
Might
Omega.
zoom it in a little bit.
Yeah, I should be able to.
It's not bad though.
I have to figure out how to move the. The problem is that the zoom controls get in the way. So I think I could double click on it, and that might.
There you go. There.
Now you're really in close.
There we go.
Yeah, there we go.
There we go. Zoomed in. So, unlike the globular cluster M13 and M3, and in previous weeks we were looking at M5, those have hundreds of thousands of stars, whether it's 200, 300, 400, or 500, as Gerald suggested, is up for debate. This one has millions of stars, and it's a much, much larger globular cluster. And there are some competing theories about globular cluster formation, and Omega Centauri may be the one that falls into the different theory of globular cluster origin, in that it might be the remnant of a galaxy that collided with the Milky Way, billions of years ago, and left its core behind, orbiting in the Milky Way's halo. So that would explain why it has so many more stars. Either that, or it was just a real massive bubble
Yeah,
of hydrogen that formed into a much larger globular cluster. Now, this is really a southern hemisphere object, but you can see it in the northern hemisphere. I've been able to see it in the month of May from the top of Mount Diablo with my telescope nearly horizontal. It's not a very attractive view of it. It's kind of loaded the horizon. I've also seen it in the Santa Cruz Mountains and in the mountains or hills outside of Livermore, where it was a little bit darker and a little bit easier to view. But yeah, if you ever make it to the southern hemisphere, then it's prominent in the sky, and it's a good reason to go to the southern hemisphere. Anyway, that's Omega Centauri.
Yeah.
How's our humidity?
Stars. Well, we are there.
We're there.
Yeah, we're at 85%.
Okay, so can we? Do you
want
to?
I tell you what.
Do you want to keep it at 85? Yeah.
Yeah. Let's take a quick look at one more item here before it gets too high here.
Okay.
I'm going to go ahead and slew.
All right.
Give us a hint. What are you going to slew to, Gerald?
A planetary nebula.
Oh.
The constellation Lyra.
Maybe
I could even guess
something that looks like a ring.
Yeah,
you got it. Yeah,
it's gonna be a ring.
So we've been doing lots of globular star clusters. Now we're going to do something different. We're going to look at the remnant of a dying star.
All right. So, are you at the spot?
Yep, we are there.
All right. Let's see what we got. Yeah, we hope, right? Let's see what we got.
So most stars do not die in supernova explosions. Common misconception is that stars die in supernova explosions. Actually, fewer than 10% of the stars in the sky end their lives in supernova explosions. Most stars end their lives in a very slow process that results in what's called a planetary nebula. So when the star gets very old, it swells up, becomes a giant star. It then begins to lose its outer layers of gas over a period of sometimes hundreds of thousands of years. And as it does so, it begins to expose the inner part of the star. And the inner part of the star is hotter. And eventually what happens is the fusion process at the center of the star. The fusion is what is the generator of the heat of the star. That fusion process stops, and whatever's left of the star collapses and becomes a white dwarf. White dwarf is very small. If you imagine the remaining mass of that star compressed down into something no bigger than the planet Earth. I think I moved the telescope while you were taking your image.
Yeah. Either that or something dramatic happened to the ring nebula at the moment we were looking at
it.
Yeah.
So anyway, the white dwarf is very small, very compact, very dense. If you can imagine a teaspoon of it weighing as much as a Mack truck, it would probably weigh even more than that. And it's radiating a lot of energy as ultraviolet radiation. And the ultraviolet radiation goes out and it hits all that gas that was expelled by the star before it became a white dwarf. And the ultraviolet radiation ionizes the gas in that cloud and causes the cloud to glow. And so what we see around white dwarfs in planetary nebulae is a glowing cloud of gas and dust, often very symmetrical in shape. And the Ring Nebula is one of the most famous of these. It's also known as M57, Messier 57. And it is in the constellation Lyra. The Ring Nebula is about 2,400 light years away. And if you look carefully, you can just barely make out the white dwarf at the center of the donut hole. And
Yeah.
collecting images here, and he's probably going to.
I am. I was actually reading one of the questions, which was really interesting. And we'll get to that in a minute.
Okay.
So right in the center of the crosshairs is where you will see, I'm going to move it away now. You'll see a white star there. Let me see if I can enhance this a little bit. You might be able to see the white star a little bit. Not really. It kind of gets faded out. There we go.
I'm not sure how well it shows up on Facebook and YouTube.
Yeah, I'm looking at it right now. It's kind of tough. That's about as good as I'll get it.
Yeah. Maybe on the next go around, you take a little bit longer exposure, and you might be able to pick it up.
Yeah.
It actually doesn't look too bad. I'm looking at YouTube, and
now if you look at this image, you see what looks like kind of a turquoise colored ring, and around the perimeter of that turquoise colored ring, you see a red periphery, a red border. Those colors tell us about the gas in the cloud. The red part represents hydrogen. Hydrogen, when it's ionized, it glows in a couple of colors, one of which is a very distinct reddish color. But it's being overwhelmed closer in by another gas, oxygen, and a certain kind of oxygen. It's what we call doubly ionized oxygen. And that's pretty unique. We don't normally find doubly ionized oxygen glowing like this in the laboratory because the electrons shift too quickly in the laboratory. But out in space, things are far enough apart because it's mostly a vacuum that doubly ionized oxygen can stay ionized long enough to produce this glowing color. Now, you might think because the turquoise color is so bright that oxygen is the dominant gas, and it turns out that's not the case. What's happening is that oxygen, when it's ionized like this, it glows really, really bright, whereas the hydrogen, when it's ionized, it glows in that red color, but not nearly as bright. So closer in, where there's more ultraviolet radiation and the gas is denser, the oxygen dominates the color, even though it's not the dominant gas. So, still not seeing that white dwarf very well, are we?
Yeah, it's a little tough tonight for whatever reason.
Well, because
I know the reason.
Yeah.
Wind.
Yeah. Well, I can get it to a point where it shows up okay. You get enough contrast. But I don't know if you're seeing it on your cell phones. Yeah, I could try that. Yeah.
Yeah.
You can still hard to see.
There it is.
Just barely make out a little smudge in there.
Yeah.
Yeah, on a really good night with really good seeing, we can actually make out the white dwarf at the center. Yeah. But tonight, with the wind
it's a little tough.
And the humidity, we're not doing so well.
All right. Oh well, colors are nice.
But when we're looking through an eyepiece using this telescope, we don't actually see the central star either. We have to use a photograph in order to see it. It's just that dim.
Well, it's summer when you could see the Ring Nebula, but you wouldn't know it from the temperature right now.
No.
The Ring Nebula is in the constellation Lyra. The brightest star in the constellation Lyra is Vega. Vega is a type A star that's 25 light years away. Actually, it's about 25.2 light years away. And it's a relatively young star. Vega is spinning very rapidly, so much so that it's slightly squished because it's spinning so fast. And Vega is one of 3 stars, each in a different constellation, that forms a asterism we call the summer triangle. So there's the constellation Lyra, the bright star Vega, there's the constellation Cygnus, and the bright star Deneb, and then the constellation Aquila, the bright star Altair. And those three stars, Vega, Deneb, and Altair, form the summer triangle. So when we can start seeing those uh, constellations, we know it's summertime and we can look for the summer triangle. Now, summer triangle is way too big for us to see with this telescope. That's something you have to look at with your naked eye because they are pretty far apart.
What's our humidity at? And the reason I'm asking is there's something very close by that might be worth taking
We're
a look
still at
at.
85.
Well, we just hit 86, but well, go ahead.
Yeah, go ahead.
You know, there is a carbon star in. There's actually a couple carbon stars in Lyra and or Lyra, and we can. I'm trying to pick out the one that is the brightest of the three. Yeah, the brightest of the three. If I give you an SAO number, can you?
Should be able to.
Usually, yeah.
Yeah.
All right, stand by. Here we go. So this is T Lyra.
Okay.
And it's SAO Tau Lyra, SAO 67087.
670.
Mm-hmm.
87, right?
Mm-hmm.
Let me make this a little easier to read here. Okay, found it.
All right, let me.
It might be a little bit low.
Yeah, we'll see what happens.
You should be able to get it.
I'm going to give it 20 seconds. So this is somewhere. This is going to be somewhere between magnitude 7 and magnitude 9, because these types of stars, we call them carbon stars, they're variable stars, which means that their brightness changes because they're in a point in their life where they are fluctuating in size and temperature, and that causes variability. So hold on, let's see what happens here.
Have you moved the scope yet, Gerald?
Oh, yeah, I haven't moved it. I thought you had moved it. I'm sorry.
I don't think so. No.
And this carbon star has become a nebula. No, so.
Well, actually, you see off to the right in that image.
I know.
Yeah,
it looks like a carbon star.
It looks like a carbon star right there.
Yeah, right. Okay, I'm gonna go ahead and slew.
Okay.
I didn't want to interrupt you while you were.
Oh no, that's fine. You can interrupt me whenever you'd like.
That's not what you said last week.
No, that's not true.
All right, take a shot.
Well, that was during a board meeting.
So what we're going for is called a carbon star. Carbon stars typically they're relatively low mass stars, and as stars get older, they begin to fuse helium at the core, fuse it into carbon, and then the turbulence within the star mixes up that carbon and spreads it around. And carbon absorbs a lot of energy, especially a lot of light. And so it sort of creates an internal filter within the star. And so instead of the star looking white or yellow, it has this deep reddish orange color. And so we call those carbon stars. And this is a star that would be way too faint for you to see with your naked eye, but we can pick it up with a telescope. And
it is very distinct in its color. You know, it's and no stars nearby are quite that red or bright red.
One of the interesting things that most people don't realize is even on the most pristine night, if you went high up into the mountains where you had perfectly clear sky and far away from city lights, so you had no light pollution, you'd see thousands of stars in the sky. But most of the stars in the sky, that are close to us you can't see because they're these very low mass stars that don't shine very brightly. They're sort of reddish or orange in color, and they're not very hot. They're not very big. They're not very bright, but they're actually the most common star out in our galaxy.
Well, great. I'm glad we got to see that tonight.
Yeah. Well, we're up at 86, so we really should be shutting down.
All right. Well, why don't you do that, and we'll start taking some questions. I also have a couple of photographs to show if you'd like, and I'm going to go ahead and stop my share here. And all right. Now close this. So, Bob Schock, who is a regular viewer and a longtime friend of Chabot and the East Bay Astronomical Society, sent me a couple of photographs that I want to share. Let me see if I can get to them here. And open it. So what this is about is a few weeks back, actually just 2 weeks ago maybe, I was talking about how to get started with photographing astronomical objects. And I pointed out that the moon is the best target to practice with because A, it's easy to find. You don't necessarily need to hook your camera up to a telescope, although you certainly can if you wish. It's a good way to learn how to hook a camera up to a telescope if that's your preferred way of photographing the moon or other astronomical objects. And it's bright enough that you don't have to track or take painfully long exposures in order to capture a really good image. And Bob was experimenting with both his cell phone and with a camera that you can purchase to look through a microscope. There are little cameras that replace the eyepiece on a microscope. They cost about $100, and guess what? They also work in telescopes. So I guess microscopes and telescopes have pretty much the same sized eyepiece barrels, and what works in one generally works in the other. So I'm going to start by sharing a shot of the moon that he took with his iPhone. Let me get there. Here we are. And that's not bad, but you know, I tend to avoid using cell phones for photography, for night photography, because it's so susceptible to artifacts. And you can see that around the moon, there's like this fuzzy bright patch, even though the craters and the contrast of the moon itself are really great. The switch to the microscope camera though is dramatic, and you could see that putting a camera like this on a telescope makes a huge difference in quality. And I think this is just a fantastic shot, and the detail and the resolution of these craters and mountains is fantastic. And then he has another one here, which also demonstrates the same thing. These are just great.
Yeah, that's Tycho. Yeah.
Yeah, and this is with an inexpensive eyepiece camera hooked up to a telescope. Bob didn't mention which telescope, or he might have mentioned which telescope it was, but I didn't pay attention. So if you're there, Bob, go ahead and post what telescope you did that through, because I'd love to share that. A 6-inch scope. Was that a 6-inch reflector or a 6-inch refractor?
Probably a reflector, probably a Newtonian.
Yeah, I don't know what Bob has collected over the years. He is an optician.
So, guys, we just closed the telescope because the humidity got over 85%. It's now 84%.
Of course.
Oh, man. Well, there you go.
It had gotten to 86 too.
Yeah, it went up to 86, and as soon as I closed it, it went down to 84.
And that's not because the sensor is inside here. The sensor is on the roof in the building next door. So
I
not
turned off
because it
my
warms
infrared
things up.
camera. I got enough light now.
All right. Well, how are we doing on questions here?
I think
Colleen,
we have a lot of interesting questions tonight.
yeah. Colleen has a question about red and blue stars, and I think she might be a little confused on this. She says new stars are blue, older stars are red. But what in actual is going on with the ones that are flipping from blue to red? I think she might be talking about blue stragglers in globular clusters that you talked about.
Yeah. Well, let's explain something first of all.
Yeah.
The color of stars tells us the temperature of the stars. So a blue star is a very hot star, and a red star is a very cool star. A white star is sort of in the middle. So star colors are kind of the opposite of what you learn when you go into the bathroom and you look at the faucets, and the blue faucet is the cold one, and the red faucet is the hot one, and that confuses the heck out of astronomers because we know that blue is hot and red is cool. So anyway, the color tells us about the temperature. Now, in a globular star cluster, because all of the stars are very old, we assume that all of the stars should be cooler stars. And the reason for that is when a newly born star is very massive, it's very hot and it will be blue in color. But a very massive star uses up its fuel very rapidly. So a massive star may only last a few 100 million years before it ends its life. Whereas a cool star, a star with, say, the mass of our sun or even less, that star burns at a much lower temperature. It doesn't start out as being bluish white. It starts out being yellowish or white, and it lasts for billions of years. So if you take a whole bunch of brand new stars, all formed at the same time, the very massive stars are going to die relatively soon, and the low mass stars will last billions of years. So when we look at a globular star cluster that's 10 billion years old, the stars we see are all the lower mass stars that still are shining. All the high mass stars have passed away. So I hope that explains the question she's asking.
Yeah, she also mentions seeing stars naked eye flipping from blue to red. So I don't think she was.
Yeah, that's
No, that
was
doesn't
right
happen
Yeah.
in reality.
Yes.
But I'll tell you what does happen sometimes, and I don't know if this is what you're thinking of. When you are seeing a bright star towards the horizon on a night with really poor seeing, where there's a lot of atmospheric roiling, that star will appear to twinkle in many different colors. So you will see it go red, blue, yellow, red, blue, yellow, yellow, and it's not because it's actually changing color. It's because the atmosphere is refracting the light in a very rapid and unstable way. It's almost like holding a prism out in front of you and flipping it back and forth with a light in the background, and you see the different colors hit your eye very rapidly. That's what the atmosphere does when we're looking at bright stars near the horizon. And sometimes it seems like, oh, that star is changing color, when in fact obviously it's not going to be changing color. It's just going to be appearing in many different colors to us because of the distortion from our own atmosphere.
Right.
I saw a question earlier. I can't find it now. And it had to do with dark matter in the Milky Way galaxy.
Yes, I saw that. That was on Facebook, I believe.
Yeah, it was, and it scrolled off my screen, and I can't seem to retrieve it. But the question was, most of the matter that we're able to touch and see is what's called baryonic matter. It's matter that falls into the standard model of how we understand atoms and matter and the universe, and everything we interact with is baryonic matter. And dark matter is an idea that astrophysicists came up with to explain the missing mass in the universe. There was a certain amount of mass astrophysicists believe should be present in order to explain the current expansion of the universe as it relates to everything we're able to see in the night sky. And they decided, well, there's missing mass, so there must be dark matter, quote unquote. And then there's a lot of evidence that, in fact, dark matter exists. When we study the rotation of galaxies, that's one of the main ways to infer that there is matter that we don't see that is present in galaxies that affects the spin and the observations we make of those galaxies. And the question was, this is taking a long way around to the question was, is dark matter mostly non-baryonic matter, or is it mostly baryonic matter? And dark matter is considered to be non-baryonic matter. That means you can't touch it, you can't see it, you can detect it because it has gravitational effects on standard baryonic matter, but it is invisible, which is why they call it dark matter instead of light matter.
I see a comment here. Somebody wants to take a live class from us.
Yeah, I saw that.
We're really boring.
Boy, what a mistake that would be.
Yeah, we're pretty boring. You don't want to be in a live class.
There is a question here also. Why is it so humid? Where is the moisture coming from? We're in Oakland, California, just east of the San Francisco Bay. And we get a lot of wind and moisture coming off of the bay and off of the Pacific Ocean. And it comes right up to the hill here. We're on a bit of a hill. We're 1,500 feet up. And it hits the hill and it comes right up to us and stops. And we get a lot of moisture in the summer at this time of year.
Yeah, I have a friend who calls it the giant air conditioning duct.
Right.
Yeah. And we get that cool air coming off the ocean, and it causes a lot of condensation and, of course, fog.
Yeah, if you look at a map of the San Francisco Bay Area, if you look right where the Golden Gate is, that little opening in the hills there called the Golden Gate, if you draw a line straight east from the middle of the Golden Gate gap, it points right at us.
Yeah.
So when the marine layer, the cool moist air over the ocean shoots through the Golden Gate, it shoots right straight across the bay, right at us.
Yeah.
And there have been times when we are in fog here at Chabot, and you go 5 miles north, it's clear. 5 miles south, it's clear. But right here, because that finger of fog goes straight across the bay, right at us, we're in the middle of the fog. It's the fickle finger of fate.
Right. I don't know if you're able to see the whole history of questions on your screen. I know on my phone I can't.
Which one? Facebook or
Facebook?
YouTube?
Mine cut off really early for some reason. I don't know why.
I went back as far as that question on dark matter, but
anything
before that there isn't much.
Okay, so
if
anybody has a question from before that, please restate it so we can pick it up here. Facebook is.
Why wasn't Chabot built?
Right.
You don't want to go there. We can talk about that for several hours.
Here's the deal. The Chabot Space and Science Center, at the moment anyway, is part of the city of Oakland and also the Oakland Unified School District. That's going to change real soon, but right now we are a joint powers agency, part of the city of Oakland and the Oakland Unified School District. Because of that, we have to be inside the city limits of Oakland. And we are located as high and as far as we can be and still be in the city of Oakland. In fact, the parking lot where our cars are parked is not in the city of Oakland. It's in Contra Costa County. So that's how close we are to the boundary of Oakland. And so we just picked the highest and farthest point we could be and still be in the city of Oakland. So we're stuck with it.
Yeah, it's not trivial to move. So here we are.
Yeah,
Margot had a question.
Yeah.
Margot said there was an article on the Chabot Facebook site about new space probes going to Venus in the near future. Gerald, you might know more about those actual probes, so I want to preface it with just to be aware that everybody talks about how inhospitable Mars is, right? It's cold, it's dusty, the water's hard to get to, and but Mars is the garden spot of the solar system compared to Venus. Venus is an incredibly hostile environment. If the 900-degree temperatures don't get you, the hydrochloric acid atmosphere or sulfuric acid atmosphere will finish you off the rest of the way. Not to mention, if you end up buying land on Venus, it'll probably end up turning into lava and resurfacing itself in some massive lava flow long before you see the value increase. So I would just stay away from Venus. The Russians
don't buy any land there, please.
Don't buy land on Venus. The Russians were the first to be able to land a probe on Venus, and I'm trying to remember what the name of the probe was.
Venera,
that's right, the Venera probe, and it took some remarkable photographs, and I think it had a 10-minute life.
Yeah, it wasn't very long.
It wasn't very long. It really is a hostile environment, like I said. So anyway, there's now talk about going back to Venus, and I don't know much about that other than reading a cursory headline.
I think Venus is often easier to get to, isn't it, Gerald, than Mars? Typically,
it's
depending on where in a year we're talking about.
It's a shorter flight, but
but the problem is it's so difficult with that atmosphere to do anything.
So there's actually two spacecraft that are in the budget. NASA's newest budget for next year has just been put forward by the White House, and it includes funding for two Venus probes. Although the atmosphere is pretty hostile, especially when you get down close to the surface, and as Rich pointed out, the clouds covering the planet, there's a layer of sulfuric acid. But what's interesting is if you go high enough in the atmosphere, you actually find a relatively mild climate. The pressure is about the same as it is here on the surface of the Earth. And it doesn't have nearly as much sulfuric acid. So one of the proposals is to put a balloon to float around in the upper part of the atmosphere of Venus. So that's something that I think is kind of exciting. That would be pretty cool if they could put a balloon there that would just float around and take images and gather data and help us learn a lot more about Venus.
Well, that means if we were to ever inhabit Venus, it would be a Zeppelin-based society.
Yeah.
And because anywhere else would be impossible.
And then the other mission that I'm really looking forward to is the Europa Clipper.
Yeah.
The Europa Clipper is a mission to the moon Europa, which is one of the moons of Jupiter. And Europa is a moon which we believe has a subsurface ocean. Europa is completely covered with ice, but we think that below the ice there is a liquid, briny ocean that's actually warm enough to keep the ocean or the water liquid, and it's very dense in minerals, and we have some indication that there are some organic compounds. Organic compounds don't necessarily mean life, but they have the right chemistry for life. So the Europa Clipper is a mission to go to Europa and see if we can learn a little bit more about it, and maybe find evidence of life. You never know.
All right.
All right. Any other questions?
Kramer wanted to know again when Chabot's opening up, and Bob answered, and we'll answer also in November. November is the plan. So it gives us enough time to get the whole place spick and span and retool our programs and get new exhibits and all that good stuff.
Bunch of new exhibits for NASA Ames as well.
Yep.
Yeah. Well, one of the interesting things though is we're talking about the possibility of continuing to do our virtual telescope program in some way, even after we open. This is, I guess, a very popular thing that we're doing. And so there's a lot of talk about continuing, maybe not every Saturday, but certainly a couple of times a month. So looking forward to that, but it's still several months away. And let's see, somebody likes my raspy voice. I don't like my raspy voice. I don't know why you do. I had a reporter up here a couple of days ago from one of the local TV stations. She was interviewing me, and she was telling me how much she liked my raspy voice. And you guys are nuts. So anyway, one of the things we want to encourage you once more, Chabot Space and Science Center, although we are closed, but we are still doing a lot of work. We are doing a lot of construction in the interior of the facility right now, building a whole new exhibit area, bringing in some new exhibits as part of our partnership now with NASA. And because we don't have the revenue that we would normally get from ticket sales, we are relying a lot more on donations. So if you would take a moment to click on that donate button on the Facebook page, if you can, or go to the Chabot Space and Science Center website, chabotspace.org, and make a donation there, we would really appreciate it. We could use all of the support we can get. And as always, if you have an employer or you know some company that likes to support nonprofits, by all means, mention our name, Chabot Space and Science Center, and we would welcome any support. And, we like to acknowledge any corporate donations like Fremont Bank that you saw earlier. So jump on it. All right. How we doing? We answered all the questions.
I think we answered all the questions for tonight.
Okay. All right. Well, thank you, everyone. We will be
seeing
you again next week.
Nice of you to join us, and
we've got a special video that we're going to show next week as well. Yeah. So something to look forward to. So
thanks for joining us, and have a good night.